this video, we're going to take a look at kind of a summary of what we've done with evaluating definite integrals geometrically, Riemann sum, trapezoidal rule, counting blocks, and we're also going to revisit position, velocity, and acceleration to see how they connect and how we can use definite integrals to determine some of that information. So anyway, this is kind of a hodgepodge of various things. If you're in my class, do the warm-up, stop the video, do the warm-up, and then resume it to see how you did with the video. If you're not in my class, you may want to move on to the lesson. So in this warm-up, we're to set up an expression that approximates the definite integral from 2 to 6 of h of x dx using 5 sub-intervals. And just as a review and a reminder, whenever we are evaluating a definite integral, that is always giving us the net area. And so whatever area is positive stays positive, whatever area is negative stays negative. So in the first problem, we're doing that. We're accumulating that net area with a right endpoint approximation. Now notice there's no graph, there's no table, there's nothing. All we have is the name of a function, h of x. So when we approximate that area, we know that we're using rectangles because it's a right endpoint approximation. We know that we're using 5 rectangles, and we're going from 2 to 6. So let's think about that for just a second. The first thing we're going to have to calculate is what is the common width. The common width is calculated by subtracting the interval, so 6 minus 2, and we're going to divide that region into 5 parts. So 6 minus 2 is 4 divided by 5, so the common width is 4/5 of a unit. So far we know about our rectangles that the width is 4/5, and that's in common, and we know that we're going to be using a right endpoint approximation. Now the question is, how do I get to that first right endpoint? Well, let's take a look at a number line. We're starting at 2, and we're stopping at 6. That comes from the interval. We said that our common width is 4/5, so that tells us that we're going to move 4/5 of a unit away from 2/5. So if we change 2 into fifths, we'll have 10/5, which is 2, and then we're going to move 4/5 of a unit away, so that would put me at 14/5. So the first right endpoint number 1, is 14/5. Because again, how did I get that? I started at the lower bound, and I added 1 common width of 4/5. So 10/5 plus 4/5 puts me at 14/5. Now remember, that's the x value. I need the height, so I'm going to have to put that into my function, so it would be h of 14/5. Now to get to the second right endpoint, I'm going to add another 4/5, which would put me at 18/5 as an x value, and I need the height, so I have h of 18/5. So the next right endpoint puts me at 22/5, so I need the height of 22/5. Add another 4/5, and that puts me at 26/5, so h of 26/5. That's the height of the fourth rectangle. And then notice what happens when I add another 4/5 to 26/5. That gives me 30/5, and 30/5 is 6, which is the last right endpoint. So I know that I have calculated correctly because it took me to the correct last right endpoint. So this is an expression. Notice it didn't say evaluate. I don't have any way of evaluating it. It says set up an expression that approximates that definite integral using 5 sub-intervals. 4/5 is the common width. This is height number 1, height number 2, height number 3, height number 4, height number 5. And if I had a function, I could calculate that. All right, now we're going to do the same thing, but we're going to use trapezoids. We're still going to use 5 sub-intervals. We're still going to have, this time we're going to have a common height of 4/5, calculated the same way. Let's change colors here. The common height is still calculated by b minus a, 6 minus 2, divided into 5 parts, which gives me 4/5. So when I do my trapezoid, the area of a trapezoid is 1/2, that's just geometry, multiplied by the common height of 4/5, multiplied by. Now remember what we talked about with trapezoids. We're starting at 2, we're stopping at 6. Since we're doing trapezoids, and remember we've already calculated that the next stop is at 14/5. The first endpoint is used once, the last endpoint is used once, and all of the intermediate values are used twice. Okay, we've talked about that before with trapezoids. So the first base will be h of 2 plus 2 times h of 14/5 plus 2 times h of 18/5. Let me erase so I have some space here. That's 18/5. I'm just moving a common height every time, plus 2 times h of 22/5 plus 2 times h of 26/5, and here we are back to the last base, which is used only once, plus h of 6 or 30/5. And that is an expression that could be used to approximate the area under a curve using the trapezoidal rule. So that's just a generic method. They might not give you a function, they might not give you a graph, they just might give you the name of that function, and you have to set up something understanding how the common base or common height works and all that good stuff. All right, let's take a look at position, velocity, acceleration and revisit those ideas. I'm just going to kind of go through this fairly quickly because they're old ideas. We know that s of t generally represents a position function. The derivative of that is v of t, and it is a velocity function. And it's the first derivative of position. Old stuff. The second derivative of position is acceleration. Oh, I think what I wanted there is the first derivative of velocity, and which is equal to acceleration. So that's acceleration, which is the second derivative of position. Old stuff. When you find the antiderivative of little f of x, you bring back big F of x, the original function, plus c. That is a family of functions that share the same derivative. And the plus c is the constant of integration. When you evaluate a definite integral, it represents the net area bound by the curve f of x, the x-axis, x equal to a, which is the lower bound, and x equal to b. Remembering that in this case, for the net area, positive area stays positive, negative area stays negative. Just review things we've already done. And then going in reverse, if we find the antiderivative or definite integral of velocity, it represents the change in position, which is the same thing as displacement. Now we cannot use the word distance in this case because we do not know whether all of the area is positive or not. The only thing we can say for sure without seeing a graph or knowing the function is that if you evaluate a definite integral of velocity, that you will get change in position, and it is the displacement of a particle. However, if you take the absolute value of velocity, that forces any area that might be negative to become positive, and this is the change in distance. Or you could say distance traveled, but in this case, we can use the word distance because we have forced all of the area to be positive, and this would be total area, all negative area is forced to be positive, whereas the displacement is net area. Big idea to get into your brain. The antiderivative of acceleration will be change. Remember, we're going back. Change in velocity. So that would be equal to v of b minus v of a over b minus a. Okay, just review. Nothing new there. Not trying to teach you anything here. Just get it back into your brain. A key concept is, and we've talked about this in class, when you integrate a rate, you lose the rate. What am I talking about? Well, it's just a way to remember what happens. Think of velocity. If this is measured in feet per second, if you integrate feet per second, when you integrate a rate, you lose the rate. And that helps you to know what your units that you're accumulating should be. Lose the rate, what's left is what you're accumulating. Some examples. If a prime of t represents the rate of change of the area of a circle measured in centimeters squared per second, then if I accumulate, that should be, put a prime there on your paper if you don't. It should be, if I'm accumulating the area under a prime of t, then that represents, all right, so what am I actually finding here? Well, let's go back. That was centimeters squared per second was what a prime of t was measured in. So if I am integrating a prime of t, when you integrate a rate, you lose the rate, which gives me centimeters squared, which tells me I am accumulating the change in area measured in centimeters squared from 1 to 10 seconds. That's what that definite integral represents. So if you understand that idea of when you integrate a rate, you lose the rate, you can always figure out what you're actually measuring. Number 2, the graphed function represents velocity. Always write it on your graph so you can see what's going on. Of a function measured in miles per hour. So this is miles per hour, therefore the time is in hours. Write and evaluate a definite integral that represents the displacement. Key word. Always look for those key words. The displacement of the particle. And I would assume that that means from beginning to end. So that's going to be 1, 2, 3, 4. Oops, let's get rid of that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I assume it means over the whole period of time. So we want to write a definite integral for the displacement. That's very easy. We're going to go straight across net area displacement 0 to 9 v of t dt. And notice that in this, I'm going to use a triangle. So this is 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 5. So 4 times 5 is 20. Half of that is 10. In this little region right here, we have a height of 1. It's another triangle, so that's 1.5. So 3 halves times 1 is 3 halves, so that would be 3/4. All I did was 1/2 base times height, if you're wondering how I got that value. So the base is 1.5 and the height is 1, so that's 3 halves times 1 divided by 2 is 3/4. And then that last region is a triangle and a rectangle, so that's going to be 2, 1, 2, 3, 6. That region is 3, 4, 5, 6. So that total area is 6. We want the displacement, so remember everybody keeps their sign, so it's 10 minus 3/4 plus 6, which is 16 minus 3/4, which is 15, and 1/4 is the displacement. Write and evaluate two integrals that represent the total distance traveled by the particle. In other words, they're not going to let me use absolute value and kind of fudge my way through. So I have to understand that I'm going to collect the area from 0 to 1, 2, 3, 4. Actually, I fudged this a little bit. So I'm going to say from 0 to 4. So I'm just assuming, guys, watching the video, I just assumed that the graph crossed right here. It really doesn't cross at exactly 4, but let's just do that to make it easy. So 0 to 4 of v of t dt. Actually, I need more than 2 integrals. I'm going to need, how far were we going? We're going to need 3 integrals. Minus the integral from 4 to 6 of v of t, because I have to force that negative area to be positive, and then add the integral from 6 to 9 of v of t dt, because we want the total distance. Again, keywords, always important. Where's my highlighter? There it is. Total distance. So I want total area, so that'll be 10 minus negative 3/4 plus 6, so that gives me 16 3/4 is the total distance traveled. Just kind of reviewing, making sure you understand the difference between displacement and distance traveled. Let's see what else we have back here. The information that you see here is on page 17 in your packet. I strongly encourage you to take the time to read that, particularly about how you determine when a particle is speeding up and when a particle is slowing down. It is critical that you understand that when you're looking at speeding up and slowing down, you have to look at velocity and acceleration. You can't just look at velocity by itself, and you can't look at acceleration by itself. Furthermore, acceleration is not the same thing as speed. So to determine when a particle is speeding up or slowing down, you got to consider the sign of velocity and acceleration. So if velocity and acceleration have the same sign, then you are speeding up. If velocity and acceleration have opposite signs, you are slowing down. Look at the reading on page 17. There's a graph to go with it, and it helps you kind of figure out this idea and why it is what it is. So very, very, very important reading on page 17. And that's it for this video, just a review of things that we've already done.